Hi guys, so this is another one of the videos that I'm doing as a refresher video or an introductory video to what you were supposed to know about integration coming into this class. So I'm going to cover some basic rules of integration. If you're interested in the theory of integration and where it came from, then you can check out the last set of videos. So I want to talk about kind of how we do integration in practice, how we compute integrals. And the first thing that we should remember is that integrals really mean two things. So there are indeterminate integrals and indeterminate integrals are the same thing as antiderivatives. So the idea being, if you write something down like the integral of the cosine of x dx, what you're asking for is the function that when you take its derivative, you get cosine of x. So I'm going to write sine x plus c right here. And the reason that we have the plus c is that if you took the derivative of the sine of x plus c, then that would turn into the derivative of the sine of x plus the derivative of c, but the derivative of a constant is 0, and so that means this turns into cosine of x. So the derivative of sine of x plus c is equal to cosine x, and that means that the integral, or antiderivative, of the cosine x is sine x plus c. So that's the basis for this relationship. Integration undoes differentiation. The second kind of integral is called a definite integral. Sorry, I didn't mean indeterminate here. I meant indefinite. So indefinite integral is an antiderivative. The definite integral is an area. So when I write down the integral from a to b of f of x dx, the way that I interpret that is I've got some function, and I'm looking at the area between a and b contained between that function and the x-axis. So if this is f of x. Okay, so those are the two different ways that we can compute what integrals are, and we interpret integrals based on the numbers that or the form that that particular integral takes. So what were you supposed to have picked up? What rules are you supposed to know coming into this class from Calculus 1 or Calculus AB or Calculus BC? So the first thing that you were supposed to have seen coming in here is that integrals are what are called linear. So that is to say, if you have the integral of some constant c1 times f of x plus a different constant c2 times g of x, that the integral can be split up into pieces. And then once you split it up over the sum, you can actually factor the constants out. So this is the basic idea of how you can integrate or find an antiderivative for a complicated expression. So we don't often write down that this is what we're doing when we take an integral of something like a polynomial, but this really is going on in the background. So coupled with this idea of linearity, we also had some basic rules that we learned. So the rules are as follows. The integral of 0 is a constant. Because remember, what an indefinite integral is asking you is find the function that has 0 as the derivative, and the derivative of a constant is 0. Because d by dx of a constant is nothing. The integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus c, because the derivative of x to the n plus 1 is equal to n plus 1 x to the n. So the power rule for derivatives is what gives you the power rule for integrals. You can see that this is going to give you the right rule, because if you divide both sides by n plus 1, then you end up with exactly what we've written right here. Okay? So if you know a derivative rule, you can reverse it and get a rule for integrals. Okay, so let's combine these ideas. So this is the fact that the integrals are linear with the power rules here, and then we'll do some example integrals of polynomials. Oh, I should add one caveat here, which is this rule holds as long as n is not equal to -1. Okay? If you're integrating 1 over x, that turns into the natural log, but we haven't looked at that yet. That's going to be the content of chapter 6.2. Okay, so here's some basic integrals, some basic examples. If you have an antiderivative or an integral of a polynomial, then the rules of linearity say that what you're really doing here is you're breaking this thing up into pieces. And again, these are pieces that we don't usually write down because it's a lot of extra work and most people just like to look at term by term and figure out what the integrals are. But because this is sort of an example of how we get started with these rules, I'm going to lay out all the steps. Okay, so another way of writing the number 1 is that's useful for using the power rule is 1 is actually equal to x to the 0. Okay, so 1 is a number that the power rule actually applies to. So the integral of x to the 3rd dx plus 5 times the integral of x squared dx plus 6 times the integral of x to the 0 dx. And now I don't have any exponents that are negative numbers, and so that means that I can use the fact that the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1. That is, I increase the power by 1 and then divide by the new power. So this turns into x to the 4th over 4, 5 times x to the 3rd over 3, and then 6 times x to the 1st over 1, just to be consistent. And then we have to write plus c, because if we took a derivative, that plus c would turn into 0. Okay, so when we're doing indefinite integrals, we always have to write plus c, because there are a lot of functions that have the same derivatives, right, the slopes, but the only difference between those functions is what the value of the y-intercept is. So another thing that people tend to have trouble with is fractional exponents. So the idea here is that if you had something like an integral of the square root of x, that's not actually a formula you can do anything with, because the square root is a shorthand for an exponential expression. So root x really means x to the 1/2. Okay? So remember that when we're dealing with roots, that we can always turn any root expression into an exponential expression. In general, if you have the bth root of x to the a, that can be written as x to the a over b. And that means that we're going to have to do those conversions in order to use the power rule when we've got an integral involving square roots. So if you have something with a square root in it, the idea here is going to be to do something like the integral of x to the 1/2 dx. And now, because I know that the integral of x to the n is x to the n plus 1 over n plus 1, I can take this 1/2, I can add 1 to it and divide by the new power. So 1/2 plus 1 divided by 1/2 plus 1, which is x to the 3/2 over 3/2, or in most simple form, 2/3 x to the 3/2 plus c. Okay. Now you can convert that back over into square root form if you want. You could write this as 2/3 of the square root of x to the 3rd plus c. But frequently the most convenient way to write expressions like this is to write them with the fractional exponents instead of the roots. Right? They're equivalent to each other, so it's often not worth the time to go back and do that. So let's do a more complicated example of this kind of expression that involves foiling and square roots and u substitution. Okay, so how about the integral of x squared times the square root of x plus 1 dx? Now, there's not much you can do with this the way that it's written, because there's no way to get the x out from the inside of that square root. So there's no multiplication trick that's going to make this lay out correctly. Instead, a problem like this, if you don't immediately see how you can FOIL it out into a giant polynomial-looking thing or individual terms, you can actually do this problem with a u substitution. And as soon as you get the du as dx, you should be suspicious that there's going to be another substitution involving x and u here, right? So you've got u is equal to x plus 1, which is going to kill this term, and then the dx is going to get replaced by a du, but there'll still be this x squared that you have to get rid of also. So what we're going to do is we're going to take u is equal to x plus 1, and we're going to rewrite it as x is equal to u minus 1. So I'm going to do this substitution first, then I'm going to do this, and the last thing I'm going to do is I'm going to go back through and find any extra x's in the problem, and I'm going to replace them with u minus 1s. So this integral turns into a square root of u and a du, and I still have this place where the x was, right? There's an x squared here that's left over. So what I'm going to do is I'm going to take the x out and replace it with a u minus 1. On the surface, this might not look any better than the integral that we started with, except I could multiply this out, and then if I think about this as having a fractional exponent, I can distribute it in. So that I turn it into a big pile of terms that are added together. So this is u squared minus 2u plus 1 times u to the 1/2 du, and then I can take the u to the 1/2, which is what I turned that square root into, and I can distribute it in and use the rules of exponents. Remember that u of a times u of b is equal to u to the a plus b. So u to the a times u to the b is u to the a plus b. And that means that this can be rewritten as the integral of u to the second times u to the 1/2 minus 2u times u to the 1/2 plus 1 times u to the 1/2 du. And then I can combine all these exponents together using this rule and write the integral of u to the 5/2 minus 2u to the 3/2 plus u to the 1/2 du. And this is an expression that you can use the power rule on. So this can be integrated. U to the 7/2 divided by 7/2 minus 2 times u to the 5/2 minus 5/2 plus u to the 3/2 over 3/2 plus c. All I've done here is I've used the rule that the integral of u to the integral of u to the n du is equal to u to the n plus 1 over n plus 1 plus c as long as n is not -1. So I added 1 to 5/2 to get 7/2 and then divide by the new power, and so on down the chain. Because this is an indefinite integral, the last step is going to be to go back and substitute the u back in again. So I get x, what was the substitution here? X plus 1. And that's about the best you can do on this problem. So the idea is that you can't deal with anything with square roots if you don't convert over into fractional exponents. So another example that will be that will apply after we get the logarithm introduced is the following. So you could think about something like taking the derivative, say, of the natural log of the cube root of x. So there's a couple of different ways to attack this. Once we have the derivative rule, or the rules for logarithms, so this is relative to section 6.2 star, then you could write this as d by dx of the natural log of x to the 1/3. And you want to do that because once you have a 1/3 in the exponent, you can use the rules of logarithms to pull the 1/3 out. And so that means this all just turns into 1 over 3 times 1 over x. Okay, so these ideas of fractional exponents replacing roots is something that's sort of intrinsic in the way that we're approaching calculus. So you need to have facility with moving back and forth with the square roots in terms of the fractional exponents that correspond to them. And almost any computation you do is going to involve the powers and not the roots or radicals. Okay, so if any of you guys need more examples, just let me know. I'd be happy to record some more of these. But those are the basic ideas that we're going to be using in coming into the first part of Math 142. And so the basic derivative table that you picked up in your introduction to calculus should include things like d by dx of x to the n is equal to n times x to the n minus 1. That d by dx of a constant is 0, that d by dx of the sine of x is equal to the cosine of x, that d by dx of the cosine of x is equal to minus the sine of x. And then depending on where you took your class, you will have seen d by dx of e to the x is equal to e to the x, but this one we are going to do ourselves as well. You may have also seen d by dx of the natural log of x is equal to 1 over x. This is another rule that we are going to prove for ourselves because we don't assume that you've seen what are called transcendental functions yet. And that's basically the knowledge that you need coming into the class is these derivatives. And if you know the derivatives, you know the integrals because the derivative of x to the n being equal to n x to the n minus 1 implies that the integral of x to the n minus 1 dx is equal to x to the n over n. And the derivative of c being 0 implies that the integral of 0 is c. And the derivative of sine being cosine means that the integral of the cosine is the sine. And the derivative of cosine being negative sine is that the integral of the sine is equal to minus the cosine. Same thing here. The integral of e to the x must be e to the x. And the integral of 1 over x is going to be equal to the natural log of x plus c. Again, we're going to discuss these in our discussion of section 6.2, but facility with these basic derivatives is going to give you the grounding that you need to look at an integral and reverse it into an antiderivative, right? It's hard to know antiderivatives if you don't know derivatives. So please, if you need more examples, let me know, and I hope you found this enlightening.